So grab a real unmounted diamond. Just, a raw or loose stone if you have one.
Yeah, and if you don't, just imagine it.
Right, exactly. Now, gently press it against your lips or hold it flat in the palm of your hand.
You're not going to feel a normal room temperature rock.
No, you feel this sharp, almost brain-piercing chill.
It genuinely catches people off guard. I mean, if you do the exact same thing with a piece of glass or, a diamond stimulant like cubic zirconia.
You just feel whatever the temperature of the room is.
Right, but a real diamond bites back. It feels colder than actual ice.
Which is just wild. And that bizarre sensation is exactly why we're digging into this today. We've got a stack of research on the solid-state physics of diamonds. And our mission for this deep dive is to decode what is actually happening when that stone touches your skin.
Yeah, we really want to look past the sparkle.
Yeah.
Past the jewelry store displays. To see this thing for what it really is.
Yeah.
Because it is an absolute marvel of atomic engineering.
It really is. But to understand it, we have to break down some of our most basic assumptions, starting with that icy feeling on your lips.
Right, because your immediate intuitive reaction is to think, oh, this object is freezing cold.
Exactly. Like if my hand feels cold when I touch it, the object must be bringing coldness to my hand. But the research points out that this is, a complete sensory illusion.
Yeah, the diamond itself isn't cold at all. It's sitting at the exact same room temperature as the table it was resting on.
So what's happening?
What you're actually experiencing is the diamond violently absorbing your body heat. It functions like a thermal vacuum.
A thermal vacuum, wow.
It pulls the warmth out of your skin so fast that your nerve endings just fire off this distress signal, telling your brain, hey, this area is rapidly losing temperature.
So the chill I'm feeling is literally just the sensation of my own heat fleeing my body.
Exactly.
To really understand how aggressive this vacuum effect is, I think we need to look at the metric used to track it, right? Thermal conductivity.
Right. Thermal conductivity is basically a measurement of how easily heat can flow through a given material. It's measured in watts per meter Kelvin. The higher the number, the faster the heat moves.
And looking at the baseline numbers really puts the diamond stats into perspective. Let's start with air. Air is a phenomenal insulator.
Yes, thermal conductivity is tiny. It's around 0.026.
Okay, super low. And then moving up to typical solid objects, you have glass, which sits right around 1.0.
So it conducts heat, but very sluggishly. That's why pressing your hand against a thick window pane on a cool day doesn't instantly pull all the heat from your fingers.
Makes sense. And then we get into the heavy hitters, the metals.
Oh yeah, iron clocks in at about 80.
Massive jumps.
Huge. And then there's copper. We all know copper is the gold standard for this stuff. It's used in high-end cookware and computer heat pipes for a very good reason. Copper sits at about 400.
400! It is an incredibly efficient conductor. But then you look at diamond.
Yeah, brace yourself for this.
A pure diamond has a thermal conductivity rating between 2,000 and 2,200.
Which is just deeply counterintuitive.
Right. I look at a clear, transparent rock, and I'm supposed to believe it beats the best metal on Earth by a factor of 5.
It's hard to wrap your head around.
I mean, if I drop an ice cube in my hand, it steals my heat rapidly, sure, but it has to undergo a phase change. It melts to do that. The diamond is pulling heat faster than ice, faster than copper, and it's just sitting there, unchanged.
Yeah, it's an entirely passive process, but functionally devastating. So the obvious question becomes, by what mechanism is this actually happening?
Exactly. How does a crystal move thermal energy that fast?
To answer that, we have to talk about what heat actually is when it's moving through a solid object.
Let's get into that, because the physics here get a bit wild. I think most of us intuitively picture heat as a sort of invisible fluid, like a substance that seeps into an object and fills it up.
Right, like pouring water into a sponge.
Yeah.
In gases or liquids, heat is carried by molecules physically moving around and crashing into each other. But in a solid block of material, the atoms are locked in place.
They can't float around.
Exactly. They can't move freely. So, in a solid, heat is really just vibration.
Just jiggling.
Yeah. If you introduce thermal energy to a solid, its atoms start to jiggle in place. They bump into their immediate neighbors, causing them to jiggle, passing the kinetic energy down the line in a wave.
And physicists have a specific name for this wave of synchronized atomic wiggling, don't they?
They do. They call it a phonon.
A phonon.
Yeah, phonons are what we call quasiparticles. Just as we treat light as a particle called a photon, physicists treat these mechanical waves of heat and sound as virtual particles called phonons.
Because it makes the math easier.
Exactly. It makes the mathematics of how they travel much easier to calculate.
Wait, I want to make sure I'm wrapping my head around this. If I accidentally touch a hot stove or like a hot piece of metal, I'm not absorbing a heat substance. I'm just getting battered by billions of microscopic synchronized atomic vibrations.
That is exactly it. That rapid vibration transfers kinetic energy directly into the molecules of your skin. The transfer of heat through any solid material is basically a race to see how fast and how far those phonons can travel before they lose energy.
Okay, but glass and wood and plastic all have atoms that vibrate too, so why is a diamond so much faster at passing the wave along?
That's a great question.
Actually, I would assume that because a diamond is so incredibly dense and hard, it would be harder for a heat wave to get through. I picture it like trying to punch a wave through a solid brick wall versus a mattress.
That is a very common assumption. It feels like a stiff, rigid material should resist movement. But in physics, stiffness is the exact trait that allows waves to travel faster.
Wait, really?
Yeah. The speed of a phonon, which is also the speed of sound through a material, by the way, depends heavily on something called Young's modulus.
Young's modulus.
Right. It's a measurement of the stiffness of the atomic bonds. Think of those bonds as tiny springs connecting the atoms together.
So if the springs are loose, like in a block of rubber, a vibration on one side takes a while to travel because the slack in the spring absorbs the energy.
You've got it. But if you have a material where the springs are incredibly tight, pulling tautly on the atoms, nudging one atom instantly yanks on the next one with almost zero delay.
And the springs inside a diamond are about as tight as they get.
They are covalent bonds. The carbon atoms in a diamond are sharing electrons in this rigid three-dimensional tetrahedral grid. In the realm of chemistry, this is the strongest, stiffest way atoms can connect to one another on Earth.
Wow. And because of that insane stiffness, the wave transfers almost instantaneously. The research notes that the speed of sound, and therefore the speed of our heat-carrying phonon inside a diamond, is 18,000 meters per second.
Which translates to nearly 65,000 kilometers per hour.
That number is hard to even conceptualize.
It really is.
It's 3.5 times faster than sound moves through solid iron, so when that diamond touches your lip, the warmth from your skin doesn't just passively seep into the stone. It triggers a physical vibration that gets rocketed through the internal structure at 65,000 kilometers per hour.
It's an absolute autobahn for heat. But raw speed is only half of the thermal conductivity equation.
Right, because going fast doesn't matter if you crash into a wall.
Exactly.
Yeah.
Going fast doesn't matter if you constantly hit roadblocks. And this is where the diamond's second major advantage comes in. A phonon needs to travel a long distance without scattering.
Scattering meaning the wave bouncing off things and losing its momentum.
Yes. Think about typical insulators, like glass or wood. On an atomic level, their internal structures are totally chaotic.
How so?
Well, wood is full of different complex molecules, air pockets, and irregular boundaries. Glass is an amorphous solid. Its atoms are just jumbled together without a repeating pattern.
I see. So if I try to send a phonon wave through glass, it's like a bucket brigade trying to put out a fire, but the people passing the buckets are a disorganized, panicked crowd.
That's a perfect analogy.
They're bumping into each other, dropping buckets, and the water, or in this case, the energy gets lost.
Exactly. Every time the phonon hits an irregular atom, a molecular boundary, or an impurity, it scatters. It loses energy. In physics, we say the material has a very short, mean free path.
Mean free path, meaning the distance a particle can travel before colliding with something.
Right. But a diamond doesn't have a chaotic crowd. A pure diamond is a flawless crystal lattice made entirely of carbon.
It's just a pure grid.
It's an atomic masterpiece. Every single carbon atom is exactly where it's supposed to be, perfectly spaced in a repeating pattern that extends in every direction.
No impurities at all.
Right. There are no missing bricks. There are no stray elements getting in the way.
So going back to the bucket brigade, the diamond is a line of people standing shoulder to shoulder, arms locked, perfectly spaced, passing those buckets down the line with absolute military precision.
With zero drop buckets. Because the lattice is so pristine, the phonon's mean free path is massive. It can travel an incredible distance in a perfectly straight line without ever hitting an obstacle.
Okay, so we put the formula together. Thermal conductivity relies on speed and distance.
Right.
The diamond's covalent bonds give it the highest speed limit in the universe, and its flawless carbon grid gives it an open road with zero traffic. You multiply those two traits together, and you hit that thermal conductivity rating of 2200.
It behaves like an absolute thermal superconductor.
Which brings us to the most fascinating paradox of the diamond. I mean, if it behaves like an elite supermetal for moving heat, just crushing copper's performance, you have to wonder about its other properties.
So this is where it gets really interesting.
Because normally, those things are a package deal. Copper is famous for pulling heat away from things, but it's equally famous for conducting electricity. They almost always go hand in hand in metals.
They do.
So the logical assumption is that a diamond, being the king of heat transfer, should also be an incredible electrical conductor.
It makes complete sense to assume that, but it is fundamentally incorrect. The sources call this the miracle imbalance.
Miracle imbalance. I love that phrase.
It's very fitting. To understand why diamond shuts down electricity while screaming heat through its core, we have to look closely at the mechanism copper uses.
Okay, let's look at copper. How is it moving heat if it isn't using these super stiff atomic springs?
Metals have a completely different internal architecture. They contain what physicists call a sea of free electrons.
A sea of free electrons.
Yeah. In a block of copper, not all the electrons are tightly bound to individual atoms. Many of them are free to drift through the metal like a fluid.
So when I introduce heat to a copper wire, what happens to those floating electrons?
They absorb the thermal energy and physically zip across the metal. They act like tiny delivery trucks, carrying the heat from the hot side to the cold side.
Oh, wow.
And because electrons are negatively charged particles, this exact same swarm of free electrons is what carries an electrical current when you plug a wire into an outlet. The free electrons do both jobs simultaneously.
So copper's secret is that it outsources the work to these loose, mobile electrons.
Exactly.
But a diamond doesn't have that option, does it?
It doesn't have a single one to spare. Let's go back to those covalent bonds we talked about earlier.
The super tight springs.
Right. The carbon atoms in a diamond are gripping each other so tightly and sharing their electrons so perfectly to maintain that rigid structural grid that every single electron is permanently locked down.
So there are no delivery trucks.
None. Zero. And because there are no free electrons available to carry an electrical charge, electricity simply cannot flow through it.
The diamond is an absolute electrical insulator. That is wild. It blocks electricity completely, acting like a rubber glove. But because its physical framework is so tight, it uses pure atomic vibration to move heat 5 times faster than a copper wire.
It really is a paradox.
An electrical brick wall, but a thermal open highway.
It's a completely unique material profile. And while it's a fun party trick to freeze your lip with a gemstone, this miracle imbalance is actually a cornerstone of some of the most advanced engineering on the planet today.
I was wondering about that. Outside of making specialized jewelry tools to test if a diamond is real by checking its heat transfer, what is the practical application of this? I mean, we aren't building power lines out of diamonds.
No, definitely not. But the tech industry is relying heavily on artificially synthesized diamond films. They use these lab-grown diamonds as heat sinks or cooling pedestals for extreme technologies.
Give me an example. Where are we putting lab-grown diamond heat sinks?
Think about the ultra-high-power semiconductors used in telecommunications satellites, or the components inside massive industrial laser oscillators.
Okay, heavy-duty stuff.
It's extremely heavy-duty. These are devices that handle staggering amounts of energy and generate an immense amount of heat in just a fraction of a second.
And heat is the enemy of electronics. If you don't get rid of it, the device melts.
Right.
But why go through the trouble and expense of growing synthetic diamond wafers? Why not just stick a big block of copper on the satellite component to pull the heat away?
Because of the electrical problem.
Yeah.
If you attach a highly conductive block of copper to a sensitive high-voltage semiconductor, you risk electrical interference.
Oh, because copper does both.
Yes. Copper would conduct the electricity right alongside the heat, potentially short-circuiting the component and destroying a multi-million-dollar satellite. Plus, in space, you don't have air to help cool things down via convection.
There's no breeze.
Exactly. You are relying purely on conduction to move heat to a radiator.
Ah, I see. In a vacuum, conduction is everything. You need to pull the heat away instantly, but you absolutely cannot risk any electrical crossover.
Exactly right. Diamond is the only material in the universe that can do the job perfectly at that scale.
So they just grow it in a lab.
Yeah, they use chemical vapor deposition to grow pure carbon diamond wafers specifically for this purpose. You mount your high-power electronic component onto this diamond film. The diamond sits there, utterly deaf to the high-voltage electricity, while simultaneously acting as a hyperspeed vacuum.
ripping the thermal energy away via phonons at 65,000 kilometers per hour.
You've got it.
It effectively saves the electronics from burning themselves alive.
It pushes the boundaries of what our technology can achieve. If we didn't have a material with this specific paradoxical imbalance, certain high-powered lasers and radar systems simply couldn't operate. They would thermal throttle or melt immediately.
That completely reframes the entire concept of the stone for me. One of the sources we looked at ended with this beautiful phrasing, calling the diamond a silent orchestra of crystals.
Oh, I love that.
It makes so much sense now. From the outside, it looks completely static. But inside, it's this incredibly complex symphony of physics-locked atoms, rigid springs, and high-speed waves working in perfect harmony.
It's a powerful reminder that the things we value for their surface-level beauty often have an internal architecture that is far more impressive.
Definitely.
For centuries, human beings have valued diamonds almost exclusively for their optical properties. We care about how they bend light, how they refract colors, how they sparkle on a ring. We've turned them into symbols of romance and status.
But the optical beauty is almost just a side effect of its physical perfection.
Right. The real majesty is structural. Beneath the sparkle is a thermal highway, operating at speeds that defy intuition, all while remaining electrically dead silent.
It's incredible to think about. So, the next time you find yourself holding a real diamond, remember the invisible mechanics at play. The moment that stone touches your skin, you are initiating a high-speed communication game among billions of carbon atoms.
Just by touching it.
Right. Your body heat is being converted into phantom waves, tearing through a flawless atomic grid faster than a bullet, just to disappear into the room.
It really changes how you perceive the physical world around you.
It does, and it leaves me with one final thought to ponder. Right now, this technology is largely reserved for satellites and high-end industrial lasers, as you mentioned.
Yeah, mostly specialized gear.
But lab-grown diamond technology is getting cheaper and more efficient every year. What happens when this scales down to everyday tech?
That's a fascinating question.
Imagine a near future where the processing chips inside our laptops and smartphones are mounted on or even integrated with diamond wafers instead of traditional silicon and metal heat sinks.
It would change electronics entirely.
We could be looking at a world where devices never overheat, never thermal throttle, and completely eliminate the need for bulky, noisy cooling fans. The next computer you buy might just have a diamond heart. Let that sink in.